Hi everybody, welcome back to Decaf-Math ASMR and a very warm welcome if you are new here. It's wonderful to have you join me here today. This video is going to be a bit random, I know, because I am mashing up several topic requests because I felt like this would be a fun way to touch on several of them at once. So, feel free to just zone in and out as you please. This isn't a lecture or anything. It's not a tutorial or anything either. So I hope that this is especially relaxing and kind of interesting too. So the main focus is going to be to help our friends here who are preparing to take geometry this next semester. And the request was to go over topics to know before taking geometry. So all I really have to say about that is to know everything up to or through Algebra 1 and maybe Algebra 2, depending. So I would just follow your school's curriculum if you're in school, because those topics kind of vary a little bit. Since they wanted a specific list, I went ahead and printed out just from a random source. I don't even remember what it is, but I printed out a list of Algebra 1 topics. And we'll kind of skip over some because I don't think they're really relevant to geometry, but we can do a quick little rundown. And so we're not going to stick straight on the list. And I also just realized while I was trying to save paper, and I printed it on the back of some piano sheet music. Looks like Tiny Dancer. So it's kind of hard to see the list anyway because that's a lot of notes, but whatever. So we'll just kind of look at this list. I will kind of read off of it for a little bit and to keep it kind of more relaxing rather than just, these are all the things you know, and, you're not horrible if you don't remember any of this. You're not horrible and stupid if none of this is ringing any bells. So do not worry, this isn't meant to overwhelm you. I'm just hoping to trigger some, general topics and words and phrases to kind of help you get a feel for what to know and what you might want to go back and take a look at. And on that note, I've actually already covered many of these on this channel, so feel free to check out the pre-algebra and algebra playlist because you'll see that some of them are a bit familiar as well. So while I read this list or the topics, I will be brushing with this brush, super sparkly. So I will be doing a little bit of mic brushing as well, just to remind you to not worry about all of these topics. And also, I've been wanting to play with some classic ASMR triggers anyway and experience them myself. So else will I get to do that when actually practicing math? So that's what we'll do here. A little bit of mic brushing, a little bit of topic reading. And then someone else actually requested to go over a little bit of non-Euclidean geometry, which I'm very excited about. I'm glad to have an excuse to revisit it a bit. I took non-Euclidean in college and also in high school in a different context, but it's been a long while, and I'm actually excited to go back into some concepts there. But for today, I thought that it would be a fun kind of connection to go over Euclid's postulates, Euclid's 5 postulates, and so I've written them out on these cards here, and we can go through them together. And basically, the difference between Euclidean geometry, which rely on these 5 postulates, and non-Euclidean is the 5th postulate. So we kind of play around with the 5th one and not having it, and introduce different kinds of geometries. So I thought that we would introduce geometry a little bit and make the connection to non-Euclidean geometry by talking about those today. So of course down the line we can go back into some concepts of non-Euclidean, but we'll just see when that comes up again. So I hope that that sounds good to you. I realized I pretty much spent a video's worth of time describing what I was planning on doing, but I felt like I wanted to explain why this video seems so random. So let's get to some brushing and chatting. I'm just going to be looking at this list here. So okay, I see why people like this sound. So, as I said, as I read out all of these topics or kind of ramble about some of them, don't worry about whether or not you know them. Be kind to yourself if you don't. This isn't meant to just be a list of all these things that you don't know, and maybe it'll be kind of nostalgic too if you have taken these classes. But really what I'm hoping is that sometimes when you learn a new class like geometry, sometimes if you're having a hard time in the class, it's not necessarily the class that you're in, but it might have something to do with not having the foundation. And especially for a class like geometry, it's actually kind of like its own class. It has new theorems, new concepts, new ideas, and logic. But a lot of times the problems involve algebra. So like to actually complete the rest of the problem, the setup might be a concept from geometry, but to solve it might involve some algebra. So if you're struggling in it, it might actually be the algebra part. So it might be helpful to kind of know this list ahead of time so that you know where to look or review or dig into some more if you do run into some problems. So No judgment here, no stress here. And of course, I'm your math friend, so you can just poke me if you're like, what? I don't know any of these. Don't worry. Poke me in the comments. I'm here for you. So, I would say, of course, starting with numbers, arithmetic, addition, subtraction, division, multiplication, working with fractions and decimals, percents, absolute values. So that involves addition or positive and negative numbers, exponents, just random words here, random words. And then for algebra, we have equations and expressions. So we introduce variables and combining like terms and simplifying stuff and solving the equations, solving equations. Maybe one equation with one variable, how to rearrange it, how to isolate the variable by undoing the order of operations. We'll want to be kind of familiar with ratios and proportions, cross multiplication. See you tensing up a little bit there. It's okay, don't worry. And then we introduce functions, relations. So how to work with functions, how to evaluate, giving an input, getting an output. How do you graph functions? How do you plot points on the XY coordinate plane? And how y is a function of x or whatever two variables you have. Just how to work with functions in general, input, output. We'll want to know how to write them. And then we kind of start talking about different kinds of functions, which is an ongoing conversation in other classes as well. But we introduce linear functions. Linear functions. So y equals mx plus b, and with that comes graphing lines and slope and the y-intercept and point slope form and slope intercept form, how to calculate slope, if you have 2 points on a line, how to find the slope there, how to write out the equation of a line given different bits of information. See, you know way more than you thought you did. You know way more than you thought you did. I knew it. Nice. So just everything to do with, lines. And we'll also want to understand how the slopes relate for parallel lines and perpendicular lines. So parallel lines have equal slope and perpendicular lines have slopes that multiply to equal -1, negative reciprocals of each other. And after lines, we kind of talk about polynomials in general and specifically quadratics as well. So that's when we have an x squared term. And so we want to know how to solve those and work with parabolas a bit. So you can solve quadratics by factoring using the backwards FOIL method, or you can use the quadratic formula. You can complete the square, and that's pretty much it. We really just focus on solving quadratics for an Algebra 1. And for polynomials, just different kinds, different degrees, how to multiply them using our exponent rules, the distributive property, and just adding and subtracting polynomials, so combining like terms and stuff like that again. And then really getting an introduction in solving systems of equations, specifically linear equations, which is something we actually come back and revisit in other classes. But for now, an introduction to solving by substitution, solving by elimination, solving by graphing as well. We want to look at intersection points. So just understanding the general concept, the general layout there. I remember we've made a video on substitution, I believe, and this is something that we can actually just come back and do some practice problems together. I know that there are a bunch of algebra lovers, maybe haters, but algebra studiers here on the channel, so we can definitely do that. And then factoring. We love factoring around here. So factoring out the greatest common factor, doing the opposite of the FOIL method, and also just special products, like if we have a squared minus b squared, to know those formulas. So a minus b times a plus b. And yeah, that's pretty much it. That's pretty much off of this list here. It doesn't hurt to know about arithmetic sequences and whatnot. And then it doesn't hurt to kind of have a little bit of a heads up for geometry. So, because in algebra we often mention some basic shapes and concepts like areas. The area of a rectangle is length times width. The area of a circle is pi r squared. So, and then we also want like perimeter. So the perimeter of a rectangle is 2 times the length plus width in parentheses, or the circumference of a circle is 2 pi r. So sometimes you'll get a formula sheet, but it doesn't hurt to kind of remember or review some of those formulas. And so area and perimeter for the 2-dimensional shape, but for 3 dimensions we have like cylinders and spheres and stuff. That would be 3-dimensional, and prisms and cubes. So we'll want to have the idea of volume being the space that fills in the 3-dimensional shape. And just sometimes it's brought up as a random fact in algebra, but the angles inside of a triangle add up to be 180 degrees. So that's just cool to know beforehand, and I'm sure if it's super important for you to know before, your teacher would let you know, but that's usually something that's taught right in the very beginning. And of course the Pythagorean theorem. So if we have a right triangle, so with the 90 degree, the longest is the hypotenuse, the diagonal part, and so the sum of the squares of the not hypotenuse sides equals the square of the hypotenuse. And fun fact, it actually works the other way, and that's part of the other part of the theorem, is that if you have a squared plus b squared equals c squared, that you can conclude that the triangle is indeed a right triangle. So it's actually both ways, even though the first way is the most common. So, and then just lastly, it's cool to know the concept of similarity going in. So that's just when you have two things that are the same shape. So if you just have like a triangle and then you double every single length, like double each of the sides or something, you have the same shape but corresponding edges have the same ratio. That's why it's important to understand ratios, but those are called similar triangles. So just as long as there's a constant ratio between the lengths, corresponding lengths, then that's the idea of similarity. So I would say that's pretty much everything, more or less. Let me know if there's anything else that kind of comes to mind, and if you've taken geometry, if there are any other concepts that you think would be useful for our friends here. But I believe in you, and I know that you're going to do a great job, and I'm here for you. So let's move on to Euclid's 5 postulates. Hope you enjoyed the brushing. Okay, so Euclid's first postulate. I guess we should mention why we need these. So, this kind of gives us a way to define some basic words like points, lines, circles, that kind of thing. Because if we don't have like a fundamental framework, then everything that we kind of come up with later or prove later cannot rely back to our basic statements. So the idea of a point, of course we draw them as dots or lines, we just draw a line, that can actually be random. So in high school we played around with the idea of these concepts just being very arbitrary, but we want there to be something in common. Like there should be, for instance, this first one, the first postulate is that a straight line segment can be drawn joining any 2 points. So if we have any 2 points, there should be a straight line segment that can be drawn between them. So we draw points like this in a line here, but theoretically we can just define it as anything. So, we could have 2 pandas and a table between them, as long as we define, I don't know why those, but we can, as long as we define them in this way, and pandas and tables have this relation, so that there can be a table drawn between any 2 pandas. But this way we have a framework for working with points and lines, and the line segment actually, so we haven't even talked about lines yet, but the line segment is this straight thing between this dot and this dot, or these 2 points. See what I mean? We want to be able to fall back on some definition. But speaking of lines, that's a great question. Thank you. Any straight line segment can be extended indefinitely in a straight line. So now we move from segment to a line. So we have our original segment between the 2 dots. can be extended. So the segment can be extended indefinitely, so to infinity and beyond in both directions to make a line. So a line now has a definition. It's a line segment extended indefinitely in both directions. So that's postulate number 2. Very good. And now we have the concept of a circle. So number 3, given any straight line segment, a circle can be drawn having the segment as radius and one endpoint as center. So we have a straight line segment, again a segment, so just between these 2 points we have a segment. A circle can be drawn, so now we're defining what a circle is. If you recall, a circle is going to have a center. We need to define where the center of that circle is, because otherwise we'd have circles everywhere. And a set length, which is the radius. And a circle is the set of all points that are equidistant to my center. So once I set that length, I just trace out everything that is the same distance to my center. So what this is saying is that if I have a straight line segment, that's going to have a length. So that length is going to be a radius. Technically, if the length of the radius is a constant number, but it has infinitely many radii, so we just say as radius. So that segment's going to be the radius, and one endpoint is center. So I just drew it with this one, but you could make that the center and draw a different circle over here. Right, so I just did one for demonstration purposes, but you could have done it differently. And so that's it. We have a definition of a circle now. And this, when I free-handed it, it was very lopsided. So of course I made it more bold over and over again to try and fix it. And now it's less horrendous, but it's still really bad. Oh well. But you get the idea. It should be equidistant all the way around. Very nice. Now, number 4 says that all right angles are congruent. All right angles are congruent. So now we know a right angle is this 90 degree, this perpendicular thing here, 90 degrees. It's actually 90 degrees on the other side as well. So you can draw it without the little t, just that part. But 90 degrees. And so to say that it's congruent, the idea of congruence is a little bit more complicated. But the idea is just that they're all the same, right? So generally we say that there's going to be an isometry, so we map this thing and flip it, and it's this one. So we just want something that preserves distance, but we don't have to worry about that. Basically, in this case, they're all 90 degrees. So like 90 degrees is 90 degrees. They're all congruent in all right angles. So all angles that measure 90 degrees are the same. They're just kind of flipped, or maybe, arranged differently, but they're all congruent. Okay, so you don't want 90 degrees here and then you move it somewhere else and it's suddenly like 72 degrees. You don't want it to be all wonky like that. Okay, so we take that as a postulate, and that kind of gives us a definition of 90 degrees for a right angle. Now, here's postulate number 5. It's very complicated to read out loud, but let's give it a go. And this is the one that we get to mess around with a little bit for the other kinds of geometries. But if two lines are drawn which intersect a third in such a way that the sum of the inner angles on one side is less than 2 right angles, then the two lines must intersect if extended far enough. Okay, so let's look at that. If two lines are drawn, so I have this line and this line, right? 2 lines. Again, they extend however far we want by our definition of line in postulate 2. And there's a third line that crosses them both, like this, the traversal. And it crosses in such a way that the inner angles on one side, so these are the smaller angles on this side rather than these two, if they are, if the sum of those angles is less than 2 right angles, so this is less than a right angle and this is less than a right angle, then the two lines must intersect if extended far enough. So so these two add up to be less than 2 right angles. So if I extend it, you can see that they do touch. So that's all. It's just if the angles happen to add up in that way with this third line, then they must intersect. So this is equivalent to the parallel postulate actually. So you can kind of substitute postulate 5 for the parallel postulate, which says, given any straight line, so we have a straight line here, and a point not on it, so I just drew a point right there, there exists one and only one straight line which passes through that point, so here, such that through that point it never intersects the first line, no matter how far they are extended, which is our definition of parallel, right? The idea of extending it to infinity and never meeting up, never touching or intersecting is parallel. So there's exactly one line that is parallel to our original one. That's the parallel postulate, which seems kind of obvious if you think about it. In geometry, our Euclidean geometry, there's only, if we have a point here, if you draw any other line in any other way, it's going to intersect with the other one. It has to literally be in the same direction as our first line. But you think, wait, when would that ever not really be true? That's so strange. And that's when we introduce spherical and hyperbolic geometries. So if you just kind of picture putting our coordinate plane wrapped around a sphere, our whole concept of what parallel means, or even for hyperbolic geometries, a whole concept of what parallel means and what straight lines look like is a little bit distorted, because a straight line along a sphere is not going to look really straight if we draw it out, right? But the concept of parallel and intersection kind of changes. And so that last one, kind of moving it around, the concept of not having one and only one parallel line with the point off of a line, is really interesting and leads into some non-Euclidean geometries. So, but for now, that's nothing to worry about for our regular Euclidean geometry. And to anyone who is learning that very soon, I hope that you are kind to yourself, that you have fun, take your time. I'm here for you, and I love you. And